let me get that going. All right, so we are recording now. So let's circling back to what we're here for, system dynamics. I believe we ended up at kind of a mathy thing the other day, and let me get my screen share and stuff rolling here. So there'll be a little bit of mathy stuff today. This might be the most mathy talk of the whole thing. It shouldn't be too daunting, but everything's relative, right? And then we're going to really start looking at building models. So just bear with me today. And this is what we looked at last time. So I'm going to zip through this stuff here. You know, what is the computer doing? And I think we ended up right here. So we're going to talk today about or wind up our discussion of analytical versus simulated solutions, and then start looking at molecules, assemblies, archetypes, generic structures. And you're going to see, perhaps not today, but as we go along, that having a knowledge of these things is very useful when you're going to build your model of something. Because otherwise you stare at a blank screen, a white background, and it's beckoning you to do something. And if you don't have a knowledge of what others have done, what structures are out there and what have you, you're going to have to reinvent everything from scratch. Go ahead if that's your thing, but most of us will build on what others have done, right? So we're trying to set a foundation for that today, as well as finishing up our discussion of analytical and simulated solutions, and they sort of schmear, these ideas kind of schmear together. All right, so if we were to, in fact, I'm going to zip back here real quick. This whole idea of linear models and why do we care, just real quick to refresh our memory. There's a pattern here. Here's our pattern. And this is for all the flow equations in your model. If all your flow equations, so the ordinary differential equations are the flow equations in a system dynamics model, if you want to do math talk. And if all of the flow equations follow this pattern that is on your screen right now, the model is linear. So I think I probably mentioned last time that when I was first learning this stuff years ago, I thought a linear model generated a line, a straight line, either a line up, a horizontal line, or a line down. That it was the time shape or the behavior that made the model linear. And it's absolutely not. Linear models can generate all sorts of time shapes. Whether or not the model is linear is a function of this pattern. If one of your flow equations deviates from this pattern, when it's part of a loop, then the model is nonlinear, and you can't solve it analytically without either you just can't, which is most models, or there are some special cases where there's some mathematical tricks and treachery you can use to solve it analytically. But by and large, for our purposes, if it's nonlinear, you need the computer to solve it. And if it's linear, you can do it either way, on the computer or analytically with scratch paper and pencil, like you do in a calculus class. Okay? So let's just take a look at this pattern right here. And remember, the S's are stock. So this is a very, very generic, general pattern. So stock 1, stock 2, and so forth. And there's N stocks in this proposed model. And then the U's are exogenous factors. So one-way causation, something from outside the fence is shocking or driving or impinging on the model inside the fence. Those are the U's, exogenous factors. And the little A's and the little B's are simply weights or parameters. Okay? So if we have a model that has no exogenous driving factors or shocks, so all the U's disappear, And if that model has only one stock in it, S1, okay, then S2 disappears, S3, and all the S's disappear. Then I hope you agree with me that what's left is just these terms right here. The change in the stock called S1 over time is equal to some weight or parameter A1 times the stock itself, right? If all the other S's go away because there's no other stocks in the model and there's no exogenous factors in the model, most of this stuff disappears and you're just left with this stuff right here, right? Okay, so now let's go to where we left off. So that's this, that model with only S1 in it and DS1 DT. Now we've changed the names. Instead of S1, now it's called stock. And instead of DS1 DT, now it's called flow. And instead of little a1, it's called coefficient or COEF. Okay. But notice the flow equation, because the flow is D stock 1 DT or DS1 DT. It's equal to the stock S1 times little a1, right? So that's a linear model, right? And that, so this model, and here's a picture of it, and that model is identical to this thing here if S1, S2, and so forth go away and all the U's go away, just here. So that's the traditional math representation. And now we're calling it stock, flow, and coefficient or COEF instead of A1. So the names change, but what is it? You put lipstick on a pig, it's still a pig. Put lipstick on a differential equation, it's still a differential equation. Okay, so let's tap the brakes right there. Does everybody see that that's true?
Yes.
That's okay, good. So
I think Mike, I just want to add how helpful this is, Mike, because this material has been presented to me by different people in different ways. But part of the hang up for me, because I'm such a literal learner, is the way they label this stuff is not consistent. And it really scrambles my brain. Maybe other people can hang with that, but having the math and the equations and the terminology associated with a structure is really helpful.
Yeah, a lot of academic fields do that. Different authors use different terms for the same thing, and that kind of throws a curveball. You know, it's in statistics and economics, the items in a sample we call observations. In engineering, they call them samples.
I mean, that's exactly.
So we're like, our sample is full of observation, their sample is full of samples. It's like, what? You know, and that's not a huge deal, but it's things like that that throw you a little curveball when you're trying to figure out what somebody's doing.
Or people use a lot of acronyms and just assume that, you know, that was a big problem with the first time I took this course back in 2016, was they just threw around all these acronyms like everybody knew what they were talking about, you know?
Ashley's in the service, so she knows about acronyms.
You feel my pain, Ashley? Huh?
I do know about acronyms, but it has been a while since I did differential equations, so it's a different kind of acronym.
Yeah.
But it's good. It's good to review. It's coming back slowly.
Okay. So yeah, and the course is not per se differential equation, and it's just to you know, sort of tie it to the underlying math to the extent so you're aware of it. You don't have to do the underlying math. You're just aware of the connection as to what we're trying to do here. So this is the simulated representation. We're going to do the calculus here in just a minute of that linear differential equation. So here's the flow equation, as I said a couple of times here, which is the diff-EQ. The coefficient or little a1 is just a parameter or a weight, okay? And, you know, that's, you know, inside of these icons here are these equations. So later on, when we click on these icons, we're going to have to specify these sorts of equations. So it's already been done for you here, but when we start modeling, you'll see. And then the stock, really, when you plop a stock down with the software, you get two equations that are automatically generated. The first is this guy here, and then the second is this guy here. So let's do the second one first. It's the initial value. You have to tell Stella how much stuff is in a bathtub at the beginning because it doesn't know. So in order to solve a model, what does that mean? It means finding out how much stuff is in each of the system's stocks or bathtubs at every point in time. The software has to know, well, how much is in there to begin with? And then I can calculate, right? So you have to give it the initial value, okay? So that when you plop down a stock, it's going to want an initial value, okay? And then behind the scenes, it's going to generate this equation here. You may or may not see it, depending on the System Dynamics software package you're using. It may or may not look like this, and it may or may not be easy to find or see. And Stella, you can, but you got to do a little work to find it. Okay, so like when you would click on a stock over here and a window will come up or a panel will pop out, you're not going to see this here. You can find it in Stella. I'll show you when we get that far, but it's behind the scenes. But we show it here for a couple of reasons. Number one, this is what's going on. It's represented by this stock. But number two, this is Euler's method. Remember Euler's method here, right? Summing up the rectangles to get the area beneath the curve, which is the amount of stuff that flowed into the stock from time 0 to time 1, or over some dt, right? In the simplest case, the computer is adding up rectangles, the area of rectangles. Well, that's what this equation says right here. It says what's in the stock now is what was in the stock one time step ago before the computer took a simulated step forward in simulated time, plus the area of the rectangle. The flow is the height of the rectangle, and the dt is the width. So this flow times dt right here, that's the rectangle, the area of the rectangle. And you're just adding the next rectangle to what was in there before the computer stepped forward. So when it takes a step forward here, dt, it's going to take the flow, the height, times dt, that's the area of a rectangle. It's going to add it to all the other rectangles. That's what's going on here. So that's Euler's method. So the stock icon, when you see it in equation form, when you tell Stella, show me the equations rather than the stock flow diagram, it's going to show you this right here for Euler's method. And you can see that's the area of a rectangle is being added to what was in to the sum of all the other rectangles before the computer took a step. And if it hadn't stepped yet, then it has to know the initial amount in the stock. So it can add the first rectangle to it. See? By the way, let me just switch over here real quickly because I want to make something clear. Even though Stella will always show you that equation, no matter if you're using a Runge-Kutta method or what have you, it's more of a symbolic representation to represent numerical integration, the computer stepping through time and computing the area beneath the curve. But there are all different ways to do that. Euler's method is just the simplest way. Let me show you another way that's more accurate. But it's, I prefer thicker lines. I think they're easier to see here. So if we were to hand draw that situation where we have time here, and we have I got these little hitches here, but it's hard to draw with a mouse. And this is the flow or the net flow, right? And then we had something like this. And this distance here we said was dt. right? And we said, well, in the simplest case, just compute the sum of the area of one rectangle. And you say, well, that's an approximation because you got that wedge above, right? That is an error. It's an integration error. And they said, what do you do? Well, make dt smaller, right? And then you get two rectangles. The computer has to compute the area of two rectangles and add them together. More work to do, but the sum of the two wedges that generates, if you recall, is less. Well, how about this? What if we said instead, ask the computer to calculate this area of a rectangle, right? And then this area. So it's doing two rectangles now. It was doing one before, just right here in the red. Now it's going to do two. And then the green rectangle, that area, cut it in half. And then add this half of the second rectangle, add that to this. So now it's computing a trapezoid, right? And you can tell, even with my crappy artwork here, that the error now is just this little thing here relative to the previous error, which was all of this, right? This is for the same dt. So the computer would have to do more work, right? But for the same dt, you would get a more accurate estimate of the area beneath the curve, the amount of stuff that's flowed into the tub, right? And there are many other techniques that involve varying dt. It's not always the same. Or doing a Taylor series expansion and making a guesstimate about a point on the curve, and all sorts of crazy stuff. So
what's this method again, Mike? The first one was Euler's. This is
I think it's called the trapezoid method, I think.
Okay.
I think that's what it's called. I'm just trying to show you a simple way that's more accurate than Euler for the same dt, without doing all sorts of crazy Taylor series expansions. So, okay.
That's helpful to understand. I've been wanting to know what that stuff all meant, but that's very helpful to understand that.
Okay, cool.
So Euler's method uses Taylor series expansion.
No. What I'm saying is there are many numerical techniques that can be used to find the area beneath the curve on a digital computer. The simplest method is Euler's. But I said, let me show you another technique that'll use the same dt and be more accurate than Euler's, which I just showed you. You calculate a trap. Now, the computer has to do more work. So, I mean, with Euler's method, has to do more work if you make dt smaller. But for the same dt, you could see you'd get a more accurate estimate of how much just flowed into the stock. In other words, the area beneath the curve. But it's still very simple. I'm saying there are other techniques, like, for example, Runge-Kutta methods that use Taylor series expansions and variable step sizes and all sorts of other numerical treachery that computer scientists are always working on to, and it starts involving the registry of the memory of the computer and all sorts of crazy stuff that you really got to, be into computer engineering, computer science. And for certain problems, you need like extreme accuracy, right? So that's why. But for our purposes, we generally speaking don't need to do that. My world, dollars and cents kind of get me where I need to go most of the time. But I'm just calling your attention to the fact that this representation, this equation always shows up in Stella when you plop down a stock, even if you're using a Runge-Kutta method. Even if you're using not Euler's method, it shows you the equation for Euler's method because it's really a representation, like a visual cue, rather than what's going on necessarily in the guts of the software, unless you're using Euler's method. Okay.
Okay.
All right. So I'm hoping everybody kind of sees the how we're tying the computer ease, this is what a Stella model would look like to the traditional math. And then here's its stock flow representation. So there's all different ways of doing the same thing, right? Now, remember, when we solve a model, what we're saying is how much stuff has flowed or is in each of the stocks in the model at every point in time. That's the solution to a dynamic system, whether it's a difference equation, differential equation, agent-based model, system dynamic, doesn't matter. That's what it means. And we said there's two kinds. There's analytical solutions, exact analytical solutions that you do by hand, and then there's simulated solution, generally speaking, right? We said exact analytical solutions are for linear models with a few exceptions with some nonlinear treachery. And nonlinear models, you have to solve on the computer. Okay, so let's nail that down a little more concretely. So what I'm going to do here is now we got Euler's method again. So we're going to start with Euler's method here, right? And all I'm going to do is say I want anything with the word stock in it on the left side of the equal sign. So see, it says I'm just moving it over here. If you do the same thing to both sides of an equal sign, you preserve the equality. So we subtracted stock t minus dt from both sides. So all that happened there. Then I'm saying here where it says flow, I said, well, what is a flow? Flow is equal to the stock times the coefficient. Flow is equal to the stock times the coefficient. This is the same. So I just define the flow. Okay. Then I note here that stock now minus stock 1 dt ago is delta stock, or the change in the stock over one time step, right? So this is just another way of this. This is another way of representing that, the change in the stock over 1 dt. And this stuff stays the same. Now I do the treachery, the mathematical sleight of hand. Look over here, and then I pull the rabbit out of the hat, okay? Notice what I do here. I divide both sides by the stock at times t. That's not the treachery. So you get rid of it on the right, and here it is on the left. And look what I do here. There's delta, that's a d, and it's big and with points on it. So it's representing discrete changes, not smooth, continuous changes. You want a smooth d if you want to represent infinitesimally small changes. Now you can't do that on a digital computer, make infinitesimally small, but we're doing the treachery. We're going to say, but if you could, what would it look like? So I switched the d to say, now we're going to pretend the computer can take infinitesimally small steps. Okay, and then I divided both sides by stock at times t. Then you've got to have had calculus to know that we're going to have to do an integral here. And you got to do the same thing to both sides. Remember, an integral sign is an S, which means sum up or accumulate, add up, right? Now, how do you know how to solve this thing here? You just have to take a calculus class and you learn what the solution to that is. When you see that, you're taught, when you see that, ding, you're in your mind, you should say, aha, I know how to solve that.
My mind never went bing.
There's a light bulb goes off.
No.
There's most of these things have well-known solutions that mathematicians have devised over the centuries, and you just have to know them. And then once you graduate and get all your A's and whatever, then you just use the computer or the chemical. In my day, it was a chemical and rubber manual that had all the integrals in it. You just look up the one that, because it's why do you got to figure it out every time? I mean, somebody's already done it, just got to recognize what it is, right? So Dr. Pankratz taught us back in 1977, I learned this, when you see D stock over stock, think D cabin over cabin. And when you integrate it, you get a log cabin. Dave Pankratz, he just retired. He was a young'un when I was a student, but he's but anyway, that's I still remember. That's how you identify that integral. So that the solution to this integral is a log cabin. You're integrating between time 0 when you started and the present time, so you've got to evaluate the integral over that time space. Got to do the same thing to both sides. Over here, again, if you study calculus, you know that constants hook around to the left. The integral sign's a linear operator like a summation sign is, or expected value in stats. The constants hook to the left and get out of your hair. So the coefficient's gone. And then you've got a Star Trek matter, antimatter thing going on here. They wipe each other out. The antiderivative wipes out the derivative. So you're left with the T. So the S wipes out the D, you're left with the T. So there's your coefficient. There's your T that's left over. And you got to evaluate both sides between 0 and T. What that means is you plug in T, or whatever that is. It happens to be T. So you plug T into T. It's a little weird, but this could be a number that you'd plug in for T, but it's T. So you plug T in and you subtract off what you get when you plug 0 in. So you plug in T and you subtract off what you get when you put 0 in. I skipped a step here and I pulled coefficient out of there. Okay. And of course, that's just going to be coefficient times T. Again, you have to know your, in this case, pre-calculus, that rules of logarithms say you just got to recognize this. I recognize it. That when you have the difference between two logs, you can rewrite it as the log of the quotient. Okay, some mathematician proved that in, whatever, 1793 or something, who knows, right? And the coefficient times T, that's just over here. That's staying around, no biggie. Again, if you do a lot of this scratch paper goofing around in calculus class, you see a dangling ln, no good. You got to get rid of it. How do you get rid of it? Matter, antimatter. E wipes out ln, but you got to do the same thing to both sides. Natural log is now gone. What are we after? How much stuff is in the stock at any given point in time? We're after stock at times T. So you got to multiply both sides by the stock at time 0. And that's your answer. That's the exact analytical solution. And it's assuming to this, but we're assuming infinitesimally small steps on a digital computer here, which you can't do. But if you could do it, and we use the techniques from calculus. So it's exact. It tells you exactly how much stuff is in the stock at every point in time. And guess what? You can zoom to any answer you want. So if you want to know at time 5 million, how much is in the stock, you plug in 5 million, coefficient is 0.02, you plug that in, E is 2.718, you plug that in, and you plug in the initial value of the stock, and your exact answer just pops out. If you're going to simulate to the year or whatever month, 5 million, you've got to go 1, 2, 3, 4, 5, 6, all the way out to 5 million. So that's inconvenient. And your answer will not be exact. It'll be approximate. So exact solutions are nice. You can zoom right to the answer and it's exact. It's exactly how much stuff is in each of the stocks at every point in time. The problem is it's only a feature of linear models with a few exceptions for nonlinear, special cases. All right, so for example, if this model represented the stock was your bank account and the coefficient is the rate of interest and the flow is the interest you're earning on your money, and the initial value is how much money you stick in, so it's $100 in your savings account. After 50 minutes, days, weeks, we're not saying what it is, years, however the compounding is at your bank, you'd have $271.83 if you started with 100 and the interest rate was 2% compounded continuously for whatever time means. We haven't specified what time means.
For 50 compounding periods, correct?
Yeah, so 50 years, 50 days, 50 minutes, whatever we just said it's time. We didn't say what time was, weeks, days, months, whatever. Okay. All right. Now, if we were to try and simulate, so what we're instead of that, why don't we just take this model and run it in Stella? Okay, so if I used Euler's method and a DT of 0.25, I got 271,152, and the correct answer is 271,828. If I use Euler's method, but I make DT smaller, 0.0625, I get 271,658. Correct answer is 271,828. I used a second order Runge-Kutta method and the same DT of 0.0625, and I got 271,828. Correct answer is 271,828. So it's going to be inaccurate more places to the right of the decimal point. Right. So you can get pretty accurate, just not infinitesimally small accurate.
So when you're making your model and you're trying to decide whether you want to use Euler or Runge-Kutta, what are some of the decision-making points to help you make that decision? Or do you have to kind of
So
experiment?
you're going to see some of that as we go along. Euler's method is the quickest, fastest, easiest. It's the default method in all the system dynamics programs. And it has some nice features. For example, it doesn't mess with noise. So if you specify a particular kind of noise or stochasticity in your model, for example, you might say I'm modeling a bank and customers arrive at the bank with a Poisson distribution with a particular mean and a particular standard deviation. Maybe I've been observing customers arrive and I've computed the mean and standard deviation, and I want that particular probability distribution in my model. A non-Euler method can change the statistical characteristics of the noise to not that distribution. And it can mess up other things, other estimation techniques and whatever. On the other hand, models that are loaded with integration error, you're going to see my Romeo and Juliet model is loaded with integration error. You almost have to have a higher order integration method, a more sophisticated, to get rid of. So you'll see when we do that later in the course, you'll get an exploding oscillation when you run the model. The question is that exploding oscillation due to the stock flow feedback loop structure or to integration error?
Oh, okay. And you're going to teach us how to diagnose and treat that.
Yeah.
right?
And if it's due to integration error, you got to get rid of it.
Okay.
And a
Okay.
lot of
Got it.
times using Euler's method and keep making DT smaller and smaller and smaller doesn't really fix it. You really need a higher order. So it all depends on the circumstances. Okay. All right. So I think we mentioned this before. There's round off error and there's integration error on a digital computer. If you step too big, you get integration error. The wedge is too big. And if you step too small, you bump up against the ability of the machine to store places to the right of the decimal point. So you have to pick your DT accordingly. Okay. The simplest thing is run it with whatever DT you got and then cut DT in half and run it again and see if it makes a difference. If it makes it like you get a very different behavior, then you got a lot of integration error. If you have on oscillations, if you get a lot of sharp points, that tends to be a sign of integration error. Okay. Stiff systems, kind of an advanced idea that if you have fast and slow rates of change in the same model, that can be a problem. It's a problem in a lot of non-system dynamics areas, some, laminar flow and in aerospace dynamics and stuff like that. So fluid dynamics and things. So what we say is if something is moving quite slowly relative to everything else in the model, make it a constant. And there's some other tricks that you can use as well. Some software vendors like PowerSim have, I believe, I haven't looked at it recently, but they used to at least have the ability to put the fast moving stuff in one file, the slow moving stuff in another file, and then link them, and the computer synchronizes the DTs. So there's all sorts of attempts to get around this problem or what have you. So a lot of it is problem dependent. The example is that I like to use is, and I might have said this already. I think I did in this class. If you were going to model gasoline prices or oil prices, would you include oil rigs? right? I think we discussed that, and the answer is it depends. What's the time frame, right? If it's a very short time frame, you can just assume the number of oil rigs is constant rather than very slowly changing. If it's a weekly model or a monthly model, right? But if it's a longer term model, then you know the stock of oil rigs, there's new ones being built and some being decommissioned, and you can have some being turned off or turned on when they're profitable to do so. The less the wells that have the lowest yield get turned off first. You know, you can model all that stuff on a longer time horizon.
Okay, I have just one terminology question. So when you talk about a constant versus a coefficient, I get those when to use what confused.
They're really the same thing. They're just weights.
Okay, is a
Like an
coefficient,
interest rate. So how much money are you going to earn? How much interest are you going to earn on your money? If the weight is 0, the coefficient is 0, the parameter is 0, you earn nothing. If it's 2% on $100, it's $2. If it's 4%, it's $4.
a coefficient is not necessarily something that's a U, it's a complete external. Is that consistently true all the
Not a
time?
U, it was the little A's and the little B's.
The little A's and the little B's. So that's where they have, you know, their external drivers of the system.
Well, they're just weights, but
ways.
in some sense, I guess you could say they're exogenous because they're just, their values are just imposed
Right.
on the model. They're not determined by a feedback loop.
Okay.
So in that sense,
constant
parameters are
can be, though.
exogenous.
But the constants, when you use that term constant, how is that?
Constant,
same?
parameter, coefficient, they're all mean the same thing.
Okay, that's what I need to know. Thank you.
Okay. So again, here's another trick. You know, if domestic gasoline reserve or oil rigs, if that's moving slow relative to the rest of the model, you can do something like this. So there's little tricks you can use. It's kind of an advanced idea for stiff systems. Again, there's some more technical stuff here related to picking step size. Forrester always said, pick a DT that's half or less of the shortest first order delay in the system. Okay, so maybe I should have made this slide a little later. We got to really see what that means, what the time constant and all that. We're getting there, but whatever it is, I'll point it out. Make it DT half or less of that. Roger Nail also notes another thing. Roger Nail is retired now, but he was I think he was the head of modeling for the United States Department of Energy at one point. He did system dynamics energy modeling for like his whole career. So he's a really good modeler, and he writes, there's an additional complication in the selection of your DT, your step size. Since the per step round off associated with any numerical integration scheme is essentially independent of the step size being used, and therefore the total round off error normally increases with the number of steps, so how long you're simulating, the total round off error is also dependent on the stability of the integration routine used. An integration routine is said to be stable if the total error between the actual and simulated solution decreases as the simulation proceeds. So he goes on to write, after one chooses a step size, he says 1/10 the smallest delay, right? Forrester said half or less. These are rules of thumb, guidelines, whatever. The length of the run, so how long you're simulating, relative to the step size must not be excessive, or the total number of calculations will be excessive. System dynamics models, so they have therefore another rule of thumb. In modeling a dynamic phenomenon, no delays are included that are less than approximately 1/10 of the time horizon for the phenomena. So if you're modeling 100 years, no delays less than 10 years. This rule is based on the fact that phenomena of much shorter time constants normally cannot explain the behavior of interest. Okay, so again, you start getting into stiff systems and whatever. So this DT thing, there's a lot of rules of thumb, and things to take into consideration, as well as the integration technique. I find I just make DT small, like 0.125, use Euler's method, see what happens, switch it to Runge-Kutta method, run it again, and if everything looks fine, I just leave it be. Generally speaking, that's fine. You can get into all these things here, but if something still looks a little strange or goofy, then you start doing a little bit of a deeper dive, right? So it just depends. But usually you don't have to get overly worried about these things. Okay. For modeling most things. Okay, it's just some other issues. One of the things that I find at WPI when we have doctoral students doing system dynamics is that they really love system dynamics. Well, they should, because they're doing a PhD in system dynamics. So therefore, every problem is a system dynamics problem, even when it's not. Sometimes it's just not a system dynamics problem. Stop trying to make it into one. So you got to know the limitations of your tools, and sometimes you have to pick a different tool depending on what you're trying to do, right? So what are some issues with system dynamics in light of what we've just been looking at? Okay. System dynamics models are based on the continuous concept of time, but implemented, as we've said, discretely, right? Because the computer cannot take infinitesimally small steps. So the continuous flow of time is only approximated. Okay. For certain types of problems, this is not desirable. So sometimes people freak out when you say there's an outflow of people dying or moving or something, and there's 32.125 deaths. They say, how can this be? It's either 32 or 33. Now you can go philosophical and say, well, from the moment you're born, you start to die. Some of your essence goes away every day till when you pass away, it's all gone. But
Can I quote you on this example here? Is that a Radzicki example? That's
sure. Going, you know, we academics debate angels dancing on the heads of pins, right? So why not?
Gradually losing some of his or her essence or life force.
Yeah, because you're kind of squeezing the toothpaste out of a tube. There's not, you don't squeeze it like a ball pops out. It's like taffy or you know, toothpaste.
That's what happens in the morning when I try and get out of bed.
Yeah, you kind of squeeze yourself out of bed. Absolutely. But some people are bothered by this, or they're trying to match it to data and whatever. And so if that's a problem, you got to consider using some other tools. Now there are some fixes. We have ovens and conveyors and queues and other numerical treachery and whatever. But the more you start discretizing stuff, the more you're getting away from system dynamics and the continuous flow of things. And so depending on what you're doing, you might want to elect to use a different tool, a more discrete based tool. Okay, now I had a guy, his name was Eric Tamoin, smart kid. He was a PhD student. Now he's a professor out in California. And he heard me talk about this stuff, and he contacted me as a doctoral student. He was going to do his dissertation with system dynamics. Loved what I had to say. Thought it was great. Would I teach him? This was back before we had like Zoom and stuff we're doing now. So we were kind of iterating by mail and email and stuff. And so he came up with, he had some real data on production, inventory, and sales from wherever. I don't even remember where he got it, but it was actual data. It's in a spreadsheet. 3 columns of numbers. And he said, I got an issue. And I go, what's your issue? And he goes, well, look at this. He took the production data, the inflow to inventory, and he put that in a table function and literally fed it. The flow was those data points. He initialized the inventory with the first inventory number from his spreadsheet. Then he ran the model and compared the output of sales, the outflow in his model, to the sales data that he had. And he said they're not the same numbers. They're close, but they're not the same. So system dynamics is crap. And I said, no, it is not crap. But I said, you have to understand that the flows in a system dynamics model are representing instantaneous change in time. They're continuous time differential equations, right? So that's what those flow icons represent. Flow data, however, is not measured instantaneously at an instant of time. Think about it. He was freaking out about the sales data. I don't know if I can't remember if it was monthly sales or week, whatever. Let's say it was monthly sales. What is monthly or what is quarterly? What is yearly sales? December sales plus November sales plus October sales plus what is quarterly sales? January sales plus February sales plus March's sales. What is January sales? Week 1 sales plus week 2 sales plus week 3 sales plus week 4 sales. What is January 3rd sales? 8 o'clock sales, 9 o'clock sales, 10 o'clock sales, 11 o'clock sales. What is 8 o'clock sales? 7:01 sales, 702 sales, plus 703 sales, plus 704 sales, right? Notice I kept saying plus. Flow data in the real world is collected by adding. There's a sum, a summation, an integral in there. It's not instantaneous data, right? So we wouldn't expect the numbers to be exactly the same. To make them exactly the same, you'd have to kind of model for the flow data, the collection process for the flow data, right? So he just couldn't swallow that. His conclusion was system dynamics sucks because it can't exactly replicate. So again, if that bothers you or what, whatever, because the models aren't real. Did you guys know that, right? They're not real. Just saying. So the fact that they have clinkers that are unrealistic, that are artifacts of the technique, shouldn't bother you. Don't mean you, a person, because you don't criticize the not real thing by saying this thing isn't real or realistic. Well, it's not real. It's helping you to think. But sometimes they can't fathom that, and that's a problem. Then you got to move on. Other issues. System dynamics is a top-down aggregate, or models are created from a top-down aggregate perspective. As a consequence, everything in a stock is identical in a system dynamics model. Now, if it's money, cash, a dollar is a dollar is a dollar, unless you collect coins or something, but we're not talking about that. And in fact, most money is just ones and zeros on a computer screen these days. So it doesn't matter. But what if it's people or something? Then, we have men, women, rich, poor, young, old, tall, short, whatever. If that stuff matters to the purpose of your model, then you have to start thinking about doing something. You can't just smear everything together in, a stock of people. Now, if there's a modest a number of differences, like Suzanne and I were talking about dogs with fleas, dogs without fleas, own dogs, not only, there are a modest number of categories, you can do that. And you can array them, and there are various tricks and techniques that can be used. But at some point, if all those laundry list of characteristics are important to the problem, it gets really clunky in system dynamics to do it, to represent it, and you have to select something like agent-based modeling. What else? The order in which...
I just want to make this one comment. I think it's really, this is a bigger issue in the system dynamics community than what everybody tells me whenever I ask, like, why is this not used more? And I think it has so much to do with expectations. And then you find, at least I have in the last 10 years, I find people that are in love with one modeling system or another, and then they reject everything else. They get very polarized about it. And you just made a really good explanation of there's different tools for different things that are relevant to the problem. And yet you don't hear the people talking about that.
Yeah, it's hard to be really good at like 5 tools. Mm-hmm. So, you tend to pick one and get really good at it, and maybe are good at a domain area. You know a lot about a domain area, and then a tool. Maybe you learn another tool and become really good at 2 tools. But
Mhm.
most people are not good at like 5 different tools.
Yeah.
I mean, like at the highest level, at the expert level, they might be aware of the other tool. So that's why you almost have to call in somebody who's better at the other tool. You just got to
Yeah.
know enough to know that you need the other tool.
Exactly. That was exactly what I was going to say. And frequently, so much of the thinking that you're covering here in system dynamics fits extremely well with the way I was taught, and I would venture to say probably most medical professionals are taught to think and to problem solve. You know, and we're taught in school, you know, look for the most common obvious stuff, not the zebras, you know, meaning that you got to start from the most commonly occurring issues, and it's not going to be perfect. I mean, I guess your example of the guy who wanted you to teach him, and then, you know, it wasn't perfect, and so therefore he rejected the whole thing. I mean, they beat that out of you in medicine, and we kind of learn to accept if it approximates what we commonly see on a case by case basis, then it's sufficient to help us solve the problem. I guess that's why I
Yeah, and they
like
always talk about the difference between, you know, mathematicians and engineers. You know,
Mhm.
to the engineer, as long as the bridge doesn't fall down, it's good enough. And the mathematician, it's not precise enough. You haven't proved,
Yeah.
it's not proof.
Yeah. Never
Well,
thought
it's
of
different.
it. I guess it's
Different
true.
standards of what good means or
Right,
what acceptable
right.
means.
Right.
All right, so other issues. The order in which entities enter a stock is not preserved. So entities enter a stock however they enter, and then there's a mathematical mixing process that goes on, and they leave according mathematically to a probability distribution. Okay, so that for certain things that doesn't matter at all, but for other things it matters. LIFO and FIFO accounting, last in, first out, or first in, first out, makes a difference. If you're modeling a manufacturing process, and let's say there's a station where there's a glue has to be applied and set, it makes a difference if a widget has been, let's say it takes an hour to dry, it's been there drying for 2 minutes versus for 58 minutes. Big difference. So the order that they came in and got the glue applied matters. Can't just say, you leave at a probability, just well, the glue isn't set on that one, you know. Queues at a grocery store, you know, Sally's in front of Johnny, that matters. Right? Now, again, there are different kinds of stocks in system dynamics, particularly in Stella ovens, conveyors, queues that are in there to address these situations. And that tends to push the the model away from the traditional system dynamics paradigm. Now, a lot of people say, so what? Well, 1950s system dynamics, we shouldn't be doing 1950s system dynamics, or because Jay said it in Industrial Dynamics in 1961. Who the hell cares? It's not 1961 anymore. You know, Sturman a couple of years ago wrote a famous paper now, something like System Dynamics at 60. I forget the title of it. But he basically said, let me tell you what Jay would have done and Jay would have said. And he channels Jay Forrester. And it's funny, those of us who knew Jay were reading the paper going, yeah, I don't think Jay would have said that. But John saying he would have said this, he would have done that. It's like, maybe. I don't know, but sounds like not Jay. But John's vision, because Jay isn't here to stop him now, is all this stuff is okay. The definition of system dynamics can include all sorts of stuff like agent-based, discrete stuff. That's all part of system dynamics. Okay, I mean, that's probably the modern answer. And then we have these other tools and things inside of Stella. It's cool. But the traditional standard original paradigm can't handle LIFO, FIFO, queues, gluing processes, and whatever. And there have been modifications to the software and whatever by younger people who have gone beyond Jay's original ideas, and we can address it. So some of the stuff can be addressed, and other stuff even if it can be addressed, you might say there's a better software package to do that sort of thing than System Dynamics. You just kind of got to know. Our interfaces, horrible. We're recently better with Stella and Stella Architect, which allows us to build very nice simulators. I've showed you some of them already. But, you know, for the generation that's grown up, you know, sort of like being in the simulation, and they got their ocular glasses on and they're like in it, you know, our simulations seem quite tame. So I don't know what that means. You know, do we need to be working with gamers more or something? I'm not sure. Decision makers in the C-suite, in the military, the higher, they don't want to put on meta glasses or whatever. They just want like a simple dashboard with a red light, green light, or a map of the US that changes color when something's happening or something. So maybe the people that we want to work with don't need to be in the simulation like the younger kids do. But our user interfaces could be better is all I'm saying. And our spatial capabilities aren't the greatest. When we want to have a map of a real city and we want, you know, and so we have an urban dynamics model of a city, but what if we want the neighborhoods of Boston, Roxbury, Dorchester, and whatever, all in there, Southie and whatever, the North End, and stuff is happening. And you can do it, but it's really hard to do in System Dynamics. You know, people have tried to interface System Dynamics software package with geographic information systems and what have you. And with enough fiddling, you can do it. But again, it's, you know, do you want to just switch to an agent-based modeling package at that point? That's, you know, they're better at, agent-based modeling is better at spatial stuff than System Dynamics. So I have what, you know, if you want to, what if a dirty bomb goes off in Manhattan? How do you get people out of there? You know, we had 9/11, right? So there's the tunnels, there's the bridges, whatever. And what if the terrorists take out a tunnel or a couple tunnels? Now what do you do to reroute and all that? Or your Boston Marathon, where do I put the aid stations? Or off ramps on the Mass Pike or whatever, you know, all this stuff is spatially oriented, and it's System Dynamics it's difficult to handle that kind of stuff with our tools. So you might want to consider a different software package. When I talk to economists about, you know, how, hey, if I have this tool, it helps you do what you're already doing, but it's mathy. You thought you couldn't do math and do with your stuff, but you can. That whole story I told you guys earlier. Well, the economists who are in these schools of thought, some of them consider themselves to be evolutionary economists, and they deal with fundamental uncertainty. So, for example, they'll say, well, you know, certain decisions that are made to invest in plant and equipment are made in a fundamentally uncertain world. It's the difference between risk and uncertainty. Risk you can attach a probability distribution to, like an actuary would. Uncertainty you can't. So, you know, should I build this new facility? It'll take me 5 years to get it approved, permitted, designed, built, tested, and online. Will I be able to sell the widgets from that facility 5 years from now? If I think no, I'm not going to go ahead and build it. If I think well, there's got to be something that makes me pull the trigger on it. That's a fundamentally uncertain decision, right? So it's the models that would be used to represent those sorts of things are non-ergodic, which means the probability distributions, if there even is one, are not the same over time. They differ. The system evolves. The models are evolutionary. Another way of saying it is that structure causes behavior. We say that all the time in System Dynamics, but behavior causes structure. The structure of the system can mutate. It can evolve. Okay. And they'll say, can System Dynamics models, are they non-ergodic? Can they evolve? yeah, we get it, Mike. Structure causes behavior. Can behavior alter the system's structure? Essentially rewrite the equations of the model. And I'm like, no. And they're like, well, now when I would tell him that, he'd pause and he'd say, well, what does that have to do with understanding the economy? Good point. George Richardson would say, because I asked him, he said, well, the active structure of a system dynamics model evolves through shifting loop dominance and what have you. But yes, it doesn't write its own equations, right? Now, some agent-based modeling techniques can do that. Okay, they can mutate their equations, whatever, but system dynamics models cannot. So, and models that learning is kind of a evolutionary. So the evolutionary economists kind of say, well, you're kind of there, but not quite. They really want to see artificial intelligence or something, I guess, in a model ultimately. So Suzanne, go ahead.
This is very thought-provoking concept for me, in that if we're trying to model something and it models something that happens in nature, because nature is dynamic, then I think, okay, we're on the right track here. Genetics and nature's, you can just change the genetic code based on the environment that you live in. So that would be ergodic. That's a new word for me.
So
Dynamic model.
non-ergodic would be evolutionary,
Okay.
fundamentally uncertain, and you get the system evolves whichever way. It's not predictable. Who predicted the blockchain?
But you're saying
who predicted the Chat GPT or whatever? It's like these innovations happen, and your system dynamics model is not going to have an insight and predict it. Suddenly it's going to write a Chat GPT sector or something.
So you're saying that's a limitation of system dynamics.
Yeah. And the people who do evolutionary stuff, in my world, evolutionary economics, they call me on that and say, yeah, we get it. We do circular and cumulative causation, and we do pattern modeling, and you're right. They agree with me, and then they catch me on this one. So that's why I went back to Jay and I go, here's what I'm hearing. And Jay's like, that doesn't have anything to do with understanding the economy. And then George was saying, yeah, well, true, but what we're trying to do is take what we know. We don't know the blockchain before somebody invents it, so that's not going to be in our model. And our model is not going to discover the blockchain for us.
Okay, but well, I guess
take what we know and lay it out, and the machine traces through the dynamics, including shifting loop dominance and whatever. So in that sense, it endogenously evolves its active structure. That's what George.
So we're talking about how do you deal with modeling knowns and unknowns, known unknowns, that kind of thing. You can't do that in system dynamics.
I guess so. Yeah, you can add stochastic events, and I'm doing that for the undergrads, where the police are raiding the drug dealers, and they're not raiding them every third week like a clock, because then the drug dealers would know it's the third Friday of the month, they're coming. And
well, let me just give you this example. If we're modeling, I don't know, the efficacy of mice models for some type of tumor, and we breed mice to produce a tumor at a certain rate, and that we all know that the environment the mice lives in impacts their genetic code, and that over time you'll lose that mutation in a certain number of generations. If you know what rate you lose that mutation, you could work it into the model, but that's not what you're talking about here, because you don't know that when you do your first model, right?
Yeah, the model is not going to pivot, if you will, mutate, whatever you want to say, and give you a completely new, if you will,
Okay.
structure set of equations that we would represent with a set of equations that takes it in a different direction.
Okay, I get it.
You can
now.
have, as Khalid Said would say, latent structure. It's already in there, but not active. And then it might not be active at all. Then suddenly some set of circumstances happen and it activates and it does something, but you have to put it in there to begin with. You can't, the model is not going to automatically discover something and write such equations.
Okay, I get it. Thank you.
All right. So there are people working on hybrid models, probably working on figuring out how to interface this with AI in some fashion. I don't know what that means. Maybe the ultimate answer is we bag all this stuff and just do AI stuff. I have no idea. But just the broad, this is an introductory class. So we don't have to, go into the really deep into what is non-ergodic versus ergodic modeling and all that. We just want to know, be aware that not every problem is a system dynamics problem, and that there's other tools that might be able to handle some of this stuff better than SD. And at some point you punt and say, go talk to so-and-so, not me, because that person does that kind of modeling. And this sounds like it's in that sandbox and not in my sandbox. Right? Okay. So Ashley, go ahead.
Yeah, I was gonna say, like, I'd be surprised though if AI was able to actually supplant system dynamics, because it has a bias towards historics, right? Because it's only taking data that already exists, whereas systems dynamics could allow you to still explore things that are going to happen in the future. So I don't know, that'd be my thought on it, because there are some significant limitations to AI.
Yeah, I think it'll be used to assist us in building system dynamics models. Read 50 annual reports for Acme Company, summarize them, and find me the following sorts of patterns in the data that would help me build a sector of a model, or fan out and find me the data on this or that, or make some suggestions about the appropriate sectors of a telephone company. Or I just made the other stuff. I think that kind of stuff, AI can be quite useful to help somebody build a better model. But I don't think, you're right, I don't think anytime soon it's going to replace system dynamics or literally attach to Stella, and you just press a go button and go have lunch and you come back and it's built you a wonderful Stella model or something like that. I don't think that's.
I think part of the value for system dynamics is nailing Jello to the wall. If you build a model, even if you don't do system dynamics, if it's in a facilitated setting and you have a lot of moving parts, the self-discovery process of building a model, I think, is really, really valuable.
Well, that's what Jay always said. In fact, he wrote that famous little memo that we reproduced in the SD review. It's the modeling process. It's the modeling process, not a model, I think is the name of the paper. And he was alarmed that people were focusing on their model and the elegance of the model and this beautiful thing they've built where they're going to frame it in mahogany and put it on the wall and put a light on it and bow to it as they walk down the hallway. And he said, that's not where the value is. It's not with this elegant thing you've created, this entity. It's the process of understanding and struggling with the software to figure out what is the appropriate structure causing the problematic dynamics, and then what do you do about it? And he was always like, then throw the friggin' model away. You don't need it anymore once you know what to do.
Right.
Rather than bowing to it, and look at my brilliance here and, with these equations.
I don't think that's ever going to lose its value in that department.
Okay. So let's try and wrap up this sort of mathy stuff. There's a reason for this, by talking about molecules, assemblies, archetypes, and generic structures. Now, you might remember my diagram I created when I was discovering, how heterodox economists do their thing similarly to system dynamics. people and telling Jay it's not all economists will hate your stuff, only some economists. You got to talk to the right economists, so on and so forth. Well, what we're going to do is now talk about in my diagram this stuff. Previously, when we did the characteristics of complex systems, we were doing the top stuff, right? So now we're doing the middle area. Notice that when the system dynamics doctor, the system dynamics detective is at the next crime scene or seeing the next patient, there's a problem. The patient is sick. You try and figure out what is going on here, right? The physician, the detective does not do this in a vacuum. They have knowledge of generic structures or other patients that have other similar patterns, right? And then underlying principles of medicine or whatever the case may be, right? Or the same thing in economics, which was circular and cumulative causation and so forth, right? So we're going to look at this middle set of commonalities so that we're not staring at a blank canvas every time we go to build a model. Okay, so when we talk about generic structures in system dynamics, lots and lots of people just use that term. There's kind of two ways of thinking about a generic structure. Mark Paich, in the inaugural issue of the System Dynamics Review, wrote a paper on generic structures, and he lumped them into two categories: feedback structures that are transferable to new situations within a particular field. So like the urban dynamics model, it's transferable to different cities. Jack Homer's model of diffusion of new medical technologies into the marketplace, he looked at cardiac pacemakers and clindamycin, both the pill and the ointment form. So very, very different medical technologies, but the same model with only a few modifications could explain both technologies, but they were in the same field. Versus feedback structures that are transferable across fields. Okay, and this would be more in your atoms, molecules, assemblies, and archetypes bucket. Okay, so Barry Richmond called them originally atoms in the original Stella manuals. The Vensim people, including Jim Hines, called them molecules. The Stella people just came out with their version of it, of the atoms and molecules. They call them assemblies. And then there are a little bit larger chunks of feedback structures that are transferable that are known as the archetypes. And the archetypes were really popularized by Peter Senge and his book, The Fifth Discipline, that came out in 1991. Nobody knew about them until Peter wrote this very popular management book, and then they kind of everybody was doing archetypes. So these are all generic structures. These terms are bandied about, and you just have to sort of know what sort of broadly they're talking about, and then try and zero in on exactly what the author or the speaker means, because you can get a little thrown off track depending on what they're up to. So this is a figure from Vensim, and this was done by Jim Hines, and he said, all right, we know all of these chunks of stock flow feedback loop structure that we can use again and again. So it's like if you think of Lego pieces, the stocks and flows and converters and stuff are Lego pieces, and you connect them together into different chunks, not necessarily a whole model, but like I showed you that first order positive loop there before, right? So he said, we got a lot of these, so let me try and organize them. So he did, and he tried to figure out how to allow somebody to say, all right, I have the following modeling problem. Where do I look to see if somebody already knows how to do this? So if you want a bathtub to go to zero, to drain away to zero, you would start here and follow the red arrows. If you want to close the gap between, let's say, what you want and what you got, you start with the blue, or this pentagon or whatever that is, with a 2, 4, 6. What's a 6-sided thing? It's not pentagon. It's a 6-sided thing. I don't freaking know. whatever it is. You follow the blue lines and so forth.
Yeah.
Okay. And so this is a screenshot, but you could click on these in Vensim and it will take you to literally the stock flow feedback loop structure. And there'll be an explanation. This is what it's used for. Here's an example, and you can copy it and paste it into Vensim. You don't have to reinvent it. Okay. Now, just recently, the Stella people have IC Systems came out with their version of this, and they call them assemblies. So this is from the Stella software, and you can see, again, they have adjustments, change, flows. That's similar to these yellow things, these categories here. Where do I start? I need a chunk of stock flow feedback structure that does something. And then you can copy and paste it from the assemblies into your model. You don't have to reinvent it. Now, what IC Systems does is they have assemblies on their servers, and you can invent assemblies, molecules, atoms, whatever you want to call it, and post them there, and then others can grab them and use them as necessary. Okay. So again, we don't want to reinvent the wheel if somebody's already invented it. All right, so now let's recall. This is our first assembly, our first molecule, our first atom, whatever you want to call it. Okay, we've seen this already a bunch of times. It's a first order positive feedback loop system, right? We just did that. I said, pretend the coefficient is the rate of interest and the stock is your cash and whatever, right? And then we did the calculus and we came up with the exact analytical solution because this is linear, right? And here's the simulated solution. When you press the go button in Stella, here's what happened. You know, the initial value here is stock at time 0. It's right down here at time 0 and so forth, right? You know, you could, if you wanted the same graph with the exact analytical solution, you could plug in, you know, 100, 2.718, 0.02, and then have like a column of numbers for time, 1, 2, 3, 4, you know, and then just tell Excel to, you know, to plug the column of numbers in here and kick out another column, which is a stock value, and then plot it. It would look the same. If you overlaid them, the two curves would be very close, but not identical because one's an exact solution and the other's an approximate. Okay, here is another assembly molecule atom. This is probably the most widely used chunk of system dynamics code in the universe, right here. This is a first order negative feedback loop system with an explicit goal. Okay, so think thermostat or cruise control on your car or guidance system for a missile or a robot's arm that's trying to move to a desired position to grab something. Okay, so we have a goal, and that's a goal for the stock. The goal is what we want in the stock. And then here's what's actually in the stock. And if there's a gap between what you want in the stock and what you've got in the stock, that gap is closed over time. So you see that right here, goal minus stock, that's the gap, is closed over time. It's not closed instantly. Okay. Now, we're going to see as we go along, this is a proportional control structure. So it's proportional, meaning that if this gap is big, if the goal is way bigger than the stock, let's say, or way smaller, then there's going to be a big correction. The correction is proportional to the gap. It's 1 over the time coefficient times the gap. Right? So as we go along, you're going to see we use in system dynamics and in control engineering, PID, proportional, integral, and derivative control. And this is the P, the proportional control stuff. It's really quite simple. Here's what I want. Here's what I got. If there's a gap between the two, close it over time. Okay, and that's what it looks like. Kind of looks like that. except notice we got a uniflow here. We got a biflow here. In this case, the stock and filler drain through the same pipe. Because if it's above the goal, then it has to drop down to the goal. Here, it's only going to go in. Well, I guess you could have negative values going in theoretically and drain it. But it can only go one way. So far, so good? Yes, no?
Yes, it it does work. I
Okay,
wanted
so-
to ask you, could you use that sort of a structure for discrete decisions, say for, I don't know, eating ice cream or alcohol or something? Oh, I was successful.
Oh, you can discretize any of this stuff, but that starts to get away from the paradigm. But yes, you could if you wanted to,
How does that get away from the paradigm?
because we do continuous time. We don't, you don't take one scoop, 2 scoops, 3 scoops. You'd be squeezing the ice cream from a toothpaste tube into your spoon. Because a digital computer cannot take infinitesimally small steps, right?
I guess this kind of goes back to the discussion I imagine we'll have in the future, which is how do you model decisions? So,
Yeah, we haven't gotten there.
okay.
So this is a molecule or an assembly, an atom. It's a first order positive loop. It's linear, so there's its exact solution. Here's a first order negative feedback loop structure with an explicit goal. This is the most widely used molecule in all of system dynamics. It has a lot of interpretations. It's the P and PID control. It's an averaging or a smoothing process. Okay. It's a control process. So it has a variety of interpretations, but it's widely used. Not necessarily just like this. It can be modified, stuff added to it, but it's the fundamental structure of system dynamics. And here's its exact analytical solution. We will not go through the calculus here, but there's a similar process because it's linear. And here's its exact solution. Okay, so notice we were in equilibrium. The stock was at its goal. The goal jumped up suddenly for who knows what reason. And the stock slowly filled up to the higher goal. So this negative loop corrected the gap between the blue line and the red line over time. Here's the third most important or fundamental molecule or assembly, generic structure, atom, whatever you want to call it in system dynamics. So now we have a draining process. Note the uniflow. Now we're draining, right? And this is a first order negative feedback loop process with an implied goal of 0. Okay, so in this case, if I would have had the thing step down instead of up, the blue line would have gone like so. It would have looked like this, except it would have gone to this goal, not to 0, unless this goal was 0. If this goal was 0, then it would look exactly like that. So this is a special case of this, when the goal is 0. Now, it confuses people because this stock flow feedback structure does not look like this, right? This does not look like this. Yet, this is a special case of this. If this goal was 0, the time shape would look identical to this. Okay, so that's just one of those weird things. And look here, there's a feedback loop. Oh, look here. See the feedback loop? Arrow, 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 circle. Makes sense. Here, maybe a little more murky, but we've got a loop. Here we got, where the hell's the loop? Right? It's like, well, it's just an artifact of the software. That's just how it's presented. You're not going to see a circle there. You just have to know it's feedback loop. Okay, now look at this. Over here, we said without proof, I mean, the proof is here, but we didn't go through it. The exact analytical solution is here, right? That's the same thing as this one here. I mean, the equivalent thing, okay? Now we said this is the more general case of this. This is the special case when this goal is 0. So look at the exact analytical solution. If we made this goal here 0 and 0, right? 0 and 0, this is what this analytical solution is right here. All you have to do is stick zeros in for the goal. Now look at this one. Stock at times T equals stock at times 0 times E raised to the minus 1 over time coefficient times T. Looks a lot like this. If coefficient was minus 1 over time coefficient, they would be the same. This is minus because it's draining. This is implicitly a plus sign because it's filling. But otherwise, they're mirror images of one another. Okay? So in this case, it generates exponential growth, a bathtub making more of itself, right? In this case, it's exponential decay. Okay? And so it's just the mirror opposite, mirror image. This would be used, so this is a case where the thing just by existing goes away. So this could be, for example, plant and equipment that's depreciating away because it's slowly becoming obsolete and rusty and wearing out and what have you. This could be a drug that is slowly being expelled from the system through breathing and sweating and stuff like that. This could be an options contract whose time value is going away. It can be an ice cube melting on a hot asphalt driveway because somebody dropped their drink or what have you. It can be a capacitor or an inductor in a radio, and you turn the radio off and it discharges. Now this is in like picoseconds, but when it's over here, you don't want to touch it. Got to wait till the thing discharges or you get a shock, right? So all of these, notice how they're all related to one another, right? You know, this thing looks a lot like this thing, which is a special case of this thing. And these are the 3 most widely used molecules in all of system dynamics. Okay, they're all linear. So they all have exact analytical solutions. Okay. All right, now notice we got E, we got E, we got E, E-I-E-I-O. What the heck is this E that's showing up all the time? Okay, so let's try and figure that one out.
It's a natural log, right?
Well, I think was it Euler's number, technically? So let me try and give you an intuitive explanation. So if I were to say, you know, what is this? Does anybody know what that is? You know, sometimes you see this on campus, kids have stickers.
I love those.
WPI, WPI. So what is pi?
3.1428. Is that right?
Yeah. So I got married on March 14th.
No.
So in 2016, we had 3/14/16. So we had a big celebration.
That's awesome.
Not really, but good story.
That'd be pretty geeky.
Yeah. Well, I teach at a polytechnic, but everybody can do this. Tell me this. What is pi though? Not the number. What is it?
It's something to do with a circle.
The coefficient for finding the area and circumference of the circle. I think the area, right, is mainly where you
I think it's the ratio of the diameter to circumference of a circle.
There you go.
Okay,
That's
so
what you're trying to
there's
say.
a number. It's a number, but it's a thing. Like you have a tree trunk or something you could figure out. Okay, so then you get into what is E. Now we've already kind of said it's 2.718. And it keeps going, it's irrational. But that's like telling me pi is 3.1416. Yeah, but what is it? Right? So the best intuitive explanation I found is, let's go back to this banking thing. So this is time 0, and this is time 1. And let's say at your bank, you have an interest rate of 100%. That's a great bank. I want to bank there. You double your money in whatever time. This is just time. So we're not saying what time is. 1 year, 1 day, 1 minute. We don't know. But let's say it's a year. So it's 1 something of time, 1 year. Okay. So if you invest $1 at time 0, and it's compounded at the end of the year, what happens? You get your $1 back, your principal, and you get 100%. You get another $1, right? So you get a total of what? $2. Yes?
Yes.
Okay. So now what happens if you say, well, that kind of sucks that my money was being used by the bank for a whole year and I didn't see anything till, the end of the year. So what happens if I invest $1, we still got 100% rate of interest, and halfway through the 6 months, what do I have? I have my $1, but instead of 100%, I'm going to have 50% interest, 50% and 50%, right? So then I'm going to have 50 cents halfway through the year. And then it's going to compound again. So at the end of the year, I have my $1. I have my 50 cents from last time that came along, right? But the 50 cents throws off 50% or 25 cents. And my $1 throws off the $1 like last time. So what did I have here? Let's see. I got, I'm sorry, it doesn't throw off $1, it throws off 50 cents. So this 1.5 is from here. Now the $1 throws off 50 cents and the 50 cents throws off 25 cents. I have $2.25 instead of $2, right?
Because it was compounded twice in the same time
Yes.
period.
Yeah. So what if you did it, 3 times? What if you did it 4 times? What if you did it 5 times? What if you did it, 12 times every month? What if you did it 52 times every week? What if you did it 365 times every day? What if you did it continuously, taking infinitesimally small steps? You started at $2, then we went to $2.25. People think it would go to infinity. No, it goes to $2.72. Settles down. So that's E. So it's the continuous compounding value. In this case, if you had 100% rate of interest for 1 period, continuously compounded, your $1 would turn into $2.72. Okay. So that it kind of sounds like making DT smaller and smaller and smaller, but you can't get to infinitesimally small steps on the computer, but you can in the banking system. All right. So bear with me. So we say a system's time constant is the amount of time it takes the stock, the bathtub, to fill up to 2.718 times its initial value, whatever its initial value is. Okay. So notice here, so I have this model here. Okay. So the coefficient is 1, that's 100% rate of interest, right? It went from 1 to 2.718 in 1. It took 1 time period. Okay, that's the time constant. It's 1 over the coefficient. 1 over 1 is 1, right? But if the coefficient was 0.02 like before, it takes 50 periods to go from $1 to $2.72 because it's 1 over 0.02 or 50. So that's how we calculate the time cut. So remember, Jay was saying dt has to be half or less of the smallest, he said delay, but time constant in the model. Nail was talking about time constants. So the time constants are based on these coefficients or parameters or weights. And you got to make dt smaller than that. Okay, and it's related to this magic number E. Continuous compounding. Okay. Now,
Do we actually do continuous compounding in the banking system?
no, that's why you have to be, by law, they got to tell you the true rate of interest and then the market
Annual
rate of
percentage.
interest and all that because they're compounded differently.
Right, okay.
So, all right. So before we build big models, what we do in system dynamics is build little models, and hook them, test them and hook them together. Now, if you've already built the little models, the little molecules, atoms, assemblies, there's no need to rebuild them and retest them every time. You know what they do. But until you know what they do, you got to test them and know their characteristics before you hook them together to make bigger models. Because otherwise, with great enthusiasm, as fast as you can move the mouse, you build this gargantuan thing, and then you finally hit the go button and it makes all craziness. And you don't know why. And then you bring it to me and say, can you help me? And I say, sure. And I open it up and I'm like, I see this crazy thing with stuff every which way. By the way, I don't have you throw it away at that point. I say, save that. That's good brainstorming, but let's just take one little thing here and let's put in a new file. And let's look at the molecules, right? So, so big models are built from little models that have been thoroughly tested before they're hooked together, okay? One way to test them, if they're linear and they have an exact analytical solution, is to use the exact analytical solution. That's not the signature way. We're going to get, when we start using the software, I'll show you the signature way of testing molecules and little pieces of structure. But one way to do it is to use these molecules. We can learn about them, learn about what they do. Okay, so we can, speaking of these time constants, we can ask the question, how much stuff has flowed into a stock of a first order positive feedback loop system after one time constant has elapsed? Okay. Well, we can use the exact analytical solution here. We'll call the time constant capital T. And remember, we define the time constant as 1 over the coefficient. So it's 1 over the coefficient is one time constant. And looky here, of course, it cancels out. So it's e to the 1 or 2.718 times the initial value. Okay, so it's a different way of thinking. And we just did the same thing, a different way of thinking about it. Okay, now, if something is growing continuously exponentially, a common question is, how long does it take the thing to double in size? How long does it take for my money to double? How long does it take the population of China to double? Something like that. That's known as the doubling time. Okay, so here we have T sub D is the doubling time. So the stock after one doubling time is equal to what? Well, 2 times the initial value of the stock would be twice what's in the stock, at least twice from the start, right? And you can divide both sides by the stock at time 0, leaving this. And guess what? We got a dangling E. Last time we had a dangling LN and we nuked it with an E. Now we have a dangling E. We're going to nuke it with an LN, but you got to do the same thing to both sides. Okay, so we get rid of the E, which is good, and we're left with ln of 2, which turns out to be 0.69. We don't need to worry about that at the moment where we get that from. It's a natural log. We want to solve for the doubling time. Let's move the decimal point. So whatever the coefficient is, let's say it's 2% rate of interest, 0.02. multiply it by 100, move the decimal point, make it 2, divide it into 70, and that's the doubling time. So it's 70% of the time constant. Okay, so if the time constant we said was 50, where was it 50? 50, what's 70% of 50?
Um,
60 something.
35.
35, right? So 35 is about here, right? See my cursor? And that's about 2. I don't have the exact value here. So it goes from 1 to 2. Here's your doubling. Yep. So, here's your time constant. There's your 50, and here's your 35. It doubles from 100, in this case, 100 to 200. How can you use this? Well, look at this. We saw this graph before. This, I just fetched, I don't know where the hell I got this from, but I got it from somewhere. And it was the Medicare costs projected and actual, right? When they started the program in the mid 60s. And we're talking about something that's growing exponentially. Now, that's not pure exponential growth. You can see there's little segments here, but it's close enough for government work, no pun intended, right? And I know this molecule. This is all I got. I don't have the actual data points here, but I go look at 30 to 60, right? That's your doubling time, which is 5 years. Just going here is 5 years to go from 30 to 60 billion, right? So I know it's 5 years is the doubling time, and it's 70% of the time constant. Time constant is 1 over the coefficient, so the coefficient has to be 0.14. And there it is. So it got up to, I don't know what this is, 135 billion or something, right here, 135, 140 billion, something like that, right? Now, I didn't tightly fit it to that data, but I didn't have the data. But you can eyeball a graph, and just knowing that information about, or knowing that molecule, you could do this, right? How about going the other way? We have a first order negative loop, feedback loop system with an implied goal of 0. It's just the ice cube melting away, the drug dissipating from the patient, right? The capacitor and the inductor discharging from your radio when you turn it off, whatever. So how much stuff has flowed out of the stock after one time constant has elapsed? Remember, the time constant is this, in this case, is 1 over the coefficient, or the coefficient of 1 over the coefficient, or the coefficient, right? So you plug that in for capital T, and you get a -1, which is 0.37. So if you start with 100, it's going to be down to 37 after one time constant. After 2 time constants, it's 14. After 3 time constants, it's 5. Now, if you do electronics, electrical engineering, or ham radio like I do, we're taught capacitors and inductors fully discharge where it's safe to touch them after 5 time constants. So 3 gets you 95% of the way to your goal, in this case 0. It's still too much charge in there to go sticking your fingers in. They want 5 time constants, electrical engineers. But this tells you that if you have a stock and its goal, 3 time constants gets you 95% of the way to closing the gap between what you want and what you got. And the sister concept to doubling time is half-life. So how long does it take to drain half of the stuff out of the top? If you start with 100, how long does it take to get you to 50? Right. So here's your half-life. It's half the initial stock. Remember, it was twice the initial stock when we did doubling time. We just mirror images. You get rid of the stock at time 0 from both sides. We got a half and a dangling E. You got to get rid of the E and nuke it with ln. You got to do the same thing to both sides. Remember rules of logs. The difference is a quotient. So we go the other way now. The quotient leads to the differences. ln of 1 is known to be 0. Okay. ln of 2 is 0.69, it's minus on both sides, a little bit of algebra. And again, we're 70% of the time constant. So we go from 100 to 50 after the half-life, 70% of the time constant. Yeah, Ashley, go ahead.
So I just want to make sure that I understand everything correctly. So E is the essentially the rate at which things are compounding, so it's continuously compounding, right?
Yes,
And then when you add in the coefficient, is that essentially like the interest rate that you would be compounding at
yes.
in your initial
So
example?
when it was 1, it's 100%.
Right. Right.
And if it's 0.02, 2% instead of 100%, it takes longer to get to $2.72.
Okay, and so those two things together are what create the exponential curve itself.
Mhm. Yep.
Okay. All right, thank you. It's
And
been a
then-
while.
Yeah, and then this is just a mirror image, so you're draining it instead of growing it. Now, again, how can we use this? Looky here. This is just fetched from the newspaper, the Wall Street Journal. And I said 100 million, 50 million, half-life, right? So it looked to me to be 1.5 years here, right? That looks like 1.5 years if you see my cursor, right? So 0.69, 1.5, 2.17 would be the time coefficient. And you can see, you plug that in, start at 100 million, you get to 50, the right time. Now, again, this isn't a perfect exponential decay, but, just from eyeballing a graph, you can get that. Okay. I'm looking at my clock. So let me just tell you the last thing, because the next thing we're going to do, we're going to introduce the software. We're going to start modeling. So if you're eager to model, we're going to do that soon. But let me just tell you about these archetypes. And I mentioned that they got famous from Peter Senge in his book, The Fifth Discipline, right? So did the beer game. I think I told everybody that I was flying around for about 3 to 4 years right after when the book came out, because everybody wanted the beer game done, facilitated, and I was doing it all over the world. I think I told you that, right? So same thing with the archetypes. Everybody wanted to learn the archetypes because Peter popularized it. Now, since then, other archetypes have been discovered. Like with the molecules, Heinz tried to arrange them in an orderly fashion so people could say, I'm interested in this, which one do I use? People have tried to do the same thing with the archetypes. I'm most concerned about growth or fixing a problem. Look for a dominant negative loop, look for a dominant positive loop, but nothing grows forever. Limited growth archetype. My growth seems to lead to your decline. Success to the successful. I enter into a partnership of growth, but end up feeling betrayed. Accidental adversaries. So on and so forth. So you can attempt to hear about a problem and then say, rather than staring at a blank sheet of paper, there might be an archetype that I can use to think about this problem. So the archetypes are more sophisticated than the molecules, than these little chunks of structure, but they are also generic, right? They're like these, the detective or the physician doesn't go in to see a patient or a crime scene with nothing. They know the principles and they know the archetypes or the typologies or the generic structures, right? So the takeaway here is just that people have tried to organize these things so that they can be used when confronted with a problem. You just think through it. So what archetype might fit my situation? Okay. So I'm looking at my clock. I don't know that there's time to go through this. What I did was I left these boxes blank because I originally did this for a class out at the Levy Institute at Bard College in New York. And I was going to hand these out and ask the students to fill in resources to A, success of it, think of something where this is the case and write it in the boxes. Excuse me. So that's why there's these weird boxes here. Rather than show this and then have a separate handout or something. I just did it all in the slideshow. But real quick here, successful to the successful, limits to growth, competing limits to growth, tragedy of the commons, growth and underinvestment, with eroding goals, accidental adversaries, fixes that fail, shifting the burden to the intervener, eroding goals, escalation, and they're all in these red ones here. Okay, so I'm not a big fan of these. They're okay. I don't tend to think of these like the first thing that doesn't leap to mind is necessarily one of these things, but some people love these things. A lot of our graduate students love these things and they bang them out the second you say that, oh, that's the way of whatever archetype, So to each his own. I don't know if we want to go through these, their causal loop diagrams in detail next time or not, or if you want to study them on your own, you can kind of decide for yourself whether, I mean, they're somewhat straightforward. But anyway, that's the last sort of thing related to generic structure, that second layer of, the problem, the pattern model, the commonalities, and then the principles, right? And then we're going to do the bottom, the pattern modeling. How do you build an original model? And you can utilize these principles and the archetypes and molecules and whatever. Okay. So up to you. You can decide whether we should discuss these archetypes next time or not. We want to use class time for that or not.
Mm,
You don't have to tell me now. We can just go beginning
Yeah.
of class next time. You can decide.
we can probably look at them outside of class, but then bring any questions we have,
Yeah, and there's a guy by the name, I think it's Gene Ballinger.
Mhm.
Very nice guy. You've seen Gene, Suzanne.
I actually went to Gene's house and visited him in 2015 because I was so captivated by Gene.
So Gene. He's a nice guy.
Mhm.
And he is inventing all sorts of new archetypes constantly. So he has a whole YouTube thing devoted to these things, and he goes far beyond what I've shown you here, however briefly. So again, I'm not really a fan of these things. It's not that they're good or bad. It's just that I tend not to think in terms of archetypes. I do think in terms of molecules or assemblies, but I don't tend to think in terms of the archetypes. And I don't know why. I would like to, I guess. I mean, I'm not opposed to thinking that way, but they've
Archetypes.
sort of resonated with me, if that's the way to put it.
I mean, I can see how both methodologies have their strengths and weaknesses when you think about molecules. I think the bigger thing for me, or at least the way that I learn, is Gene, whenever Gene was trying to help me, he would just say, he's one of those people that's so intelligent and so smart that he's scary, and he's not a really good teacher because of that, because he can't communicate what goes on in his brain. And he said, oh, you just like start drawing it, and it doesn't matter if it's a blank page, just put something on there and do it. And it's like, Gene, I don't know what to do, and I don't know how to write the equations. This is not making any sense. And I realize now it's like, well, you can't go speak French if you don't have any idea of the structure of the language. Yeah. And so to me, this is very much.
My youngest son is a tremendous golfer, tremendous overall athlete. His older brother and me were not, sadly. And we play golf, and he'll hit a 310, and I might hit a 230, and I'm like, how do you do that? Help me. He'll be, I don't know, Dad. I see the ball, I hit it.
Mm-hmm.
He's a natural athlete. He can't break it down because he doesn't think that way. He was one of these kids. He set, like, as a junior in college, he set all the conference scoring records in soccer and all that. And then his roommate was on the tennis team. And he said to my son one day, will you come out and just hit with me? I need somebody to hit the ball back to me. And Ben said, I've never done tennis before. I don't have a racket. And the guy said, I got rackets. I got like 5 rackets. I'll give you a racket. Just hit it back to me, or even just hit it to me so I can hit it. So Ben was like, okay. And he just goes out there. He's never done it before. And he's smoking this guy. And this guy's like, you should try out for the tennis team. He goes, I've never played before. I don't even know the rules, really. He made the tennis team. He was like the 7th player as a freshman. And then he was like the number whatever player that he was like 12-4 his senior year. And he just watched somebody do it. He could make his body do he was always this natural, but he could never explain how he does it. Me see ball, me hit, that's like, and then we're sweating. We're looking at visual aids and, all these, watching YouTube videos and filming ourselves. And we're trying to get it. We can't.
That is a really good example of Gene in the system dynamics area.
Yeah.
Super delightful guy, super smart, wants to promote system dynamics, is just kind of scary how smart he is. And he's really good. He knows more about, he just prowls the internet and looks for new technology and figures out what he likes, and he goes and plays with it and stuff. He's a very intriguing individual, and I'm glad that he started to participate in the online system dynamics conferences too.
Yeah. So the point is, these archetype things, some people really love them. Some people are expanding them beyond what I just presented here very briefly. So to each his own. I would say you know about them now, and if you poke around a little bit and you say, I find these insightful and useful, well, then by all means, put them in your hip pocket and pull them out as necessary. Or like in my case, cool, don't object to them. I get it, but it's really not how I'm wired or whatever. And so I don't tend to think about them very often or whatever, but I acknowledge others do, and so.
I think Senge presented it in his book. If you know these, however many there are, 11, 18, I've heard several different numbers, you can explain 90% of the various behaviors you experience in the world. And I don't know if that's true or not. I think they are useful and they do serve a purpose, but building stuff using molecules makes a lot of sense to me as well.
All right, so let's leave it there because I'm looking at what time. All right, we're already a little bit over. So where we're headed then is, in light of all of this information you've seen, the history of the field, famous models, detailed looks into stocks, flows, feedback loops, analytical solutions. What is the computer? So now we're going to start introducing the software and beginning to build models. Guess what? We're going to build really simple little molecules first and study them all different ways, because we want to get in the disciplined habit of not connecting things together until we fully understand how they're going to behave. Because if you do not do that, you will build a gigantic Frankenstein model that nobody, including you, can understand, and it won't work right. But if you're disciplined and test before you hook together, so on, and follow sort of the best practice, most people can arrive at a decent model when all is said and done. There's a way to do it. We know enough in our field because we've been around since the 50s. We've learned enough to be able to teach people, the average person, how to build a decent model. There's a bell curve. So somebody out here is like a genius and they can build the most insightful models known to mankind. And then some people never get it, but the rest of us are in the middle, and we can be taught how to do these things at a fairly high level, but you got to be disciplined and follow the best practice, follow sort of, in some sense, the recipe or the method. And then, so we're going to try and, make sure you guys know that stuff, as well as look at more interesting models and so forth as we go along. Okay. For the second half or whatever. Where are we halfway through? We might be halfway through. So,
yeah. Yes. I had a quick question as well. I was looking at some other literature for systems dynamics. Would you recommend Thinking in Systems by Donella Meadows? It's a good book.
Yeah, she's done. She was a very good writer, very clear.
Okay.
And she was a biophysicist by training. She was on the Limits to Growth team. Dennis asked her to write the Limits to Growth book because she was such a talented writer. The Meadowses went up to Dartmouth College and were on the faculty there. And Donella said, well, you know, my students know about me. They know about system dynamics, the limits to growth and all that. So when I teach them, I'm preaching to the choir. I Donella, want to go and tell people who haven't heard about this stuff. So she resigned her professorship and she became a newspaper columnist for her town newspaper up there, like Lyme, New Hampshire, whatever, small town newspaper. But her column called The Global Citizen was syndicated by the Los Angeles Times Syndicate. So what she would do is take a problem in the news and analyze it from a system dynamics perspective. She would sometimes build a model and whatever, and then get some insights, throw away the model and write a newspaper column about it. She finished 1 year in second place for the Pulitzer Prize in economics. Robert Samuelson won it from Newsweek, won it that year. She finished second. And then she was given a MacArthur Genius Award for where they, you know, they just give you a giant chunk of money and do whatever you want with it. No strings attached. You just show up one day and say, you're a genius here. And this suitcase of money arrives. So she was a super talented, I mean, she's a biophysicist, so she was a scientist, but in a system dynamicist, but she was also a super talented writer. So reading any of her stuff is worthwhile because she's very clean and crisp and clear about stuff. So yes, I would absolutely recommend, you know, her book or books or columns. She has a collection of her columns in a book called The Global Citizen, a collection of her newspaper columns, which is very good as well. So.
And I've read that book a couple of times. I probably have given away 10 copies of it, and I have recently given it away to my new employers. So, and I refer to it a lot.
The Global Citizen or
no, Thinking in Systems.
Things. Okay, yeah.
Mhm.
Yeah, so this is, it's a good, and she was very good. She was interesting person. She got she got encephalitis, I think.
Wow.
Passed away suddenly. Yeah, that was sad.
I've got to head out and take care of dogs.
Yeah.
I'll
Okay.
see you guys next
So
week.
anyway, so yeah, so we'll leave it there and we'll see everybody next week.
All right. Have a good night.
Bye.